Hello, people. Today what we're going to be doing is we're going to be covering, 6.2, a portion of 6.2. This section is called enthalpy and calorimetry, but we're only going to focus on enthalpy because enthalpy ends up becoming a confusing word, or just students generally have a hard time understanding what this is. But let's go ahead and let's try this. Now, enthalpy has to do with the heat of a chemical, or the heat flow in a chemical reaction. I'm going to show you mathematically how that definition came to be, right? So think of the formula for enthalpy as enthalpy is equal to the energy of the system plus the pressure times the volume, right? Now, all three of these are going to be state functions. So enthalpy is also going to be a state function, and that's going to come in handy later on, right? But before we even do that, let's talk about E. Let's talk about energy, the same equation that we used and we focused on our last video, right? So energy is equal to the heat plus the work. And a little quick note, remember that work is equal to the negative P times delta V. Sorry, negative P times the change in volume. Whoa, that's a big delta. Negative P times delta V. Or you can write that as P times delta V is equal to negative work. But our energy is this. And in order to really understand enthalpy, let's make sure that P is constant, right? We're going to have a constant pressure. You're going to see a little P under here. All that means is at constant pressure. So, right here we have a formula that the change in energy is equal to the amount of work plus the heat at constant pressure. And what we're going to do is we're going to plug in the P, plug in the V, or plug in P times delta V for W. And you'll see towards the end why we're doing all of this, okay? So our change in energy is equal to, all we did is substitute the pressure times the volume in this formula, okay? But what we really want is to understand the heat flow, because if you start looking at this equation up here of enthalpy, it's starting to look kind of similar. It has similar parts. So delta H is going to be able to be explained by Q, by heat. So we have our PV, we have an E, and we have an E. So things are looking good. So let's rearrange that formula so that our Q is on the right side. And if you feel like, oh, how did you get there, Mr. Sanchez? Well, imagine subtracting QP to both sides. So now you have negative QP plus delta E is equal to negative P times delta V. All right, and you get rid of that delta E. So negative QP is equal to delta E, sorry for writing so fast, minus P. So this is negative delta E minus P delta V. So you see how this is negative, negative, and negative. Divide by a negative, and boom, you get your heat. Your heat at constant pressure, your heat flow at constant pressure is equal to your change in energy times the pressure times the volume, all right? So this now looks very, very, very similar to our enthalpy equation. And remember earlier when I said enthalpy is a state function? Well, it doesn't matter how it gets there, right? The only thing that really matters is the ending and the beginning. So we can do this equation where we take the difference of the beginning and the end so we can see how it's changed. And when we do that, our formulas begin to look very, 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 very similar. So this tells us that our delta H and our P are related when pressure, or not just related, they are the same when pressure is constant. So enthalpy is the direction and the amount of heat that flows when pressure is constant. So if you design an experiment where pressure is constant, you can calculate the enthalpy of a chemical reaction, or you can calculate the change in heat flow in a chemical reaction. So you can calculate whether a chemical process is going to release energy and how much energy it will release. All right, and that's going to be the next thing that we're going to do. So our enthalpy is equal to our heat flow at constant pressure. And take into consideration this equation that we saw earlier. If we have methane combusting and it releases energy, using this, we can calculate the starting energy, or we can determine the amount of energy that's released from this chemical process. All right, and what you're going to be doing is you're going to be using this formula here, that the change in enthalpy is equal to the enthalpy of the products minus the enthalpy of the reactants. And what this is going to give you is the amount of energy that was released or the amount of energy that was absorbed. And we're going to do a problem like that. Do I do it in our next video, or do I do it in this one? I'll do it in this one. No, I'll do it in the next video. All right. But this right here becomes a very, very important question. Very, very important equation in this chapter and future chapters. Okay, so please do not forget what enthalpy is. Enthalpy at constant pressure is equal to the amount of heat and the amount of heat in the chemical process, right? So very, very important. But this only occurs at constant pressure. Okay, at constant pressure. Hopefully that kind of explained what enthalpy is. On our next video, what we're going to be doing is we're going to be seeing the amount of energy that's released from a mass, right? So we're going to do a little bit of stoichiometry, a little bit of conversions to see that. How long has the video been? Do we do it now? Nah, we'll just do it because I think you guys just want to see a practice problem entirely on its own. Peace out, people.